See my cursor, that's nice. Yeah, so an outline of this talk. So this is both sort of a Julia seminar and a meeting for the DigiWell project. So not everything is going to be relevant to everyone, but I thought I'd talk about a few different things we've done in Julia and sort of talk about the experiences we've had. So I'll first start with a brief overview of a small package for multi-component Flash and sort of the experience developing that. I'll talk about Jutul in a bit, which is porous media or reservoir simulator written entirely in Julia. Talk a bit about how we do automatic differentiation there, and we'll show some visualization towards the end of the talk. And finally, if I have time, I'll wrap up about and talk a bit about Julia usage within the SINTEF department. So SINTEF is a large research institute with several thousand people, so I don't have a full overview, but I did a little survey in our department at least, which is about 100 people. So I feel it's worthwhile to have a slide here on why we are interested in Julia. And one of the major points there is that coupling of different codes, so C++, MATLAB, Python, Fortran, and some proprietary that are just you get executables. This is often quite time-consuming and error-prone, and it's not really what you want to be spending your time on when you're solving actual problems for industry or research. And another thing is the turnaround from prototypes in Python or MATLAB or whatever. It can be quite long if you then need to re-implement it in C++, and it's a difficult process to manage going from one code to the other and handing that off. And many applications actually require fast simulation of both large models, which we are quite used to, but also very small models. And small models are surprisingly more important than large models at the moment for us. And it's also very nice to have this built-in package and artifact system, which is important when you have lots of data and different, you want to deploy things here and there, and it just needs to work because a lot of the people we work with or deliver to are not necessarily experts in any kind of programming. And we have been sort of using it for a while, but I think Julia is maturing quickly, and I would sort of be confident to say that the disadvantages, or the advantages, I should say, now outweigh the disadvantages, which I don't think that's always been the case in the past, but I think now it is sort of past this cusp where it's really useful for applications. So flow in porous media is sort of the main topic of this goal, and I thought I'd have a slide here on basically what that is. So it is something that has a lot of different applications. So typically the Norwegian interest in the past has been on oil and gas reservoirs, so sort of safe operations, optimal operations, and understanding the process that's going on in subsurface. You have things like heat storage, where you store surplus heat from industrial processes or seasonal heat variation in the underground, and you can bring it back up at a later stage. Geothermal energy, CO2 sequestration, which is a big topic in Norway at the moment with the Northern Lights. Groundwater flow, where you're looking at sort of possible pathways for contaminants like radioactive pollutants and these things that might spread in the underground and reach an aquifer. And then it's important to have simulation models to sort of assess to the extent that is possible and possible mitigation strategies. Current topic of high interest in Europe is natural gas storage. So say that you have an unreliable gas supplier and you want to store a large amount of gas when it's cheap. Well, you can store it in the underground. And also if you have an excess of, for instance, wind or solar power, you can make hydrogen when the electricity is cheap and store this for later usage in the underground. So basically the sort of setting, I mean, we often simulate also smaller scale things, but in the reservoir setting, you're looking at things that are, maybe 1 to 100 meters in vertical height, and anywhere from 100 to 100,000 or even a million meters in extent that you're talking about that's open to free flow. It's typically made of a geologically layered structure, so you have sort of sediments that have been deposited over time, forming different types of stone that have different types of permeability and properties. And then geological processes over time, because this has gone on for millions of years, you may have faults and sort of geological features that make the grid not so nice. So when you're sort of trying to resolve this, a combination of very fine geological resolution combined with faults and structural things, and the very high aspect ratio of the models make it quite difficult to simulate. So typically, if you're so say that we think that this reservoir is an oil and gas model, you might start off with a gas cap on the top. You might have oil in the middle and some water at the bottom. You might drill wells and you inject, for instance, water to move the fluids and replace the fluids you're removing from the producer well. So this is sort of the typical simulation model you might work with if you're looking at oil and gas. So the equations for this kind of system is relatively similar between them. You might have additional things like, for instance, an energy equation if you're looking at the transport of heat, but you have general conservation equations. So something differentiated with respect to time is equal to the mass balance in and out of some control volume. And then in source terms, that might be like an aquifer or a well or something that is generating that species. So this is sort of a simple immiscible model. And then you might also have a number of species where each species might live in several different phases. So for instance, this one lives in the liquid phase and the vapor phase. You have mass fractions that sort of govern how much of the individual species is in each phase. And the velocities here are given by a special variant of Darcy's law, which is to say that things flow against the gradient of pressure, but the gradient of pressure might depend on the phase you're in due to capillary pressure and also the density of the different phases. You sort of have counter-current flow. And you have a bunch of closures to close this system. It's not completely closed, but you say that, okay, mole fractions sum up to 1, saturation sum up to 1 in a volume, and you have some relationship for the capillary pressure, and there are different variants you can substitute in. So the multi-component flash I'll talk about first is just a small demonstration package that we use to so not doing the whole flow thing, but it answers this quite specific question. So given that you have m different species and you have the molar fraction of each of these, under isochoric conditions for pressure and temperature, you put this in a box, and you know the temperature and pressure of the box. How does that, what ends up being in the box? So do you get 2 distinct phases? For instance, does it split into gas and liquid, or does it remain a single phase? If it splits into multiple phases, how do the species distribute between the phases? And what are sort of the properties of the resulting mixture? So what's the density, how much volume is occupied by each phase, and so on. So this is basically a 2-phase flash problem, and it's quite a standard one. The governing equations is basically just a local mass balance inside that volume, saying that the sum of fractions should sum up to 1, and there should be balance between them. And the typical equation that is sort of complex there is the balance of fugacities between the 2 phases, which is basically the first order Gibbs energy minimization. And you have a lot of equations here, but they're not really that complicated. It's just a bunch of polynomials with a few exponents thrown in. So this is yeah, sorry. No. Yeah, so typically you end up with this cubic polynomial, and then there's some sort of math to pick the right roots and so on. But it's not a very complicated set of equations, but it's complex in terms of emergent behavior. So to perform a flash, you do something like this. You first determine the stability of the systems. You say, okay, is this going to split into 2 phases, which is basically checking if there exists some small volume of another phase, lighter or heavier in terms of the free energy, then seeing if that is stable. And if that is the case, you perform a solve, which is either going to be a successive substitution, which is a slow and conditionally stable version, or a Newton solve for this guy. And from that, you can get all of the roots. So you have this tight inner loop that is, yeah, I mean, it's straightforward to iterate, but you're going to iterate many times. So an example just of how you can use this module to do this is basically you say, okay, I just want the properties of methane and decane. I define that as a mixture, and I choose the equation of state. You can then define conditions. So this is the conditions of our box, pressure and temperature and mole fractions. So 4 moles of methane per 6 moles of decane. You define some conditions and you flash it, and you get out a vapor fraction, which tells you sort of how much how much vapor there is per mole of total mass. And we can go a bit further. We can say, okay, I want some extra outputs. I want the equilibrium constants. And from the equilibrium constants, you can get the liquid mole fractions, telling you how much there is of the light and heavy component in each phase. So, and the vapor mole fractions, which is how much of the heavy or how much of the components are in the vapor phase. And you see, like, one of the components is really doesn't want to be in the vapor phase. It's a heavy component. And from this, you can then, for instance, generate these phase diagrams. So a phase diagram tells you the saturation of the two-phase region. So you have outside here, you have a single phase region, a critical point over here. So for varying pressure and temperatures, this is for a fixed composition. You can generate these diagrams and say, so, okay, how does this fluid behave under different pressures and temperatures? And this flash, so solving a flash for the SP5 benchmark is a standard sort of 6-component benchmark. You have less than 20 microseconds to solve the entire flash system, which is quite good, I think. And you have some options to use, like static arrays and doing in-place updates if you really want to get fast flashes. So it is quite flexible in that you can just call the flash, but if you need to call it a million times, then there are options for doing it in place. And in terms of sort of implementation and user experience, it was quite nice. The first implementation of this was done in just a few evenings. And as you can see here on the right-hand side, I mean, it's just basic polynomials, and the equations are similar between the sort of mathematical description and what's in the text. The only thing that is sort of unergonomic if you come from a MATLAB or Python background is that while the functions themselves do not have too much in terms of type annotations, you need to make sure that the types are concrete, which is I think typical stumbling block if you sort of, yeah, you start to use MATLAB, use Julia just like MATLAB, and you might run into this. But once you resolve that, I think the results are pretty good. I think the development environment is pretty good, not quite full Visual Studio good. For instance, the debugger works, but it's to get into more complicated problems, the debugger is not a super pleasant experience. Yeah, so that's sort of context for one of the building blocks that we use to build the reservoir simulator is to have a flash available. So the next thing I'll talk about here is basically Jutul, which is I would say it's an experimental framework for differentiable finite volume simulators. Typically, reservoir simulation is done with finite volume. So the key thing here is that it's supposed to be modular because you have a lot of different variants of these models that you need to swap in. And I don't think there's a point of writing a Julia code if the performance isn't good. A large part of this, although not the only part, is to have fast linear solves. So we do linear operators and for the linear systems with basically without fill-in Schur complement, which is the fastest way to incorporate facilities and wells and so on. And we have support for different preconditioners. I'll show that in a little bit. So in terms of demonstrators on top of this, we have a few staples from textbooks, heat equation and so on. The reservoir simulator, which is called Jutul Darcy, and it's supported by this multi-component flash package. And we also have an experimental battery simulator that mirrors some of the modeling efforts we're mostly doing in MATLAB at the moment, where we're sort of testing this code on a subset to see sort of the performance and things. So here's an example that we have seen. Those of us who work in the DigiWell project have seen this many times. It's a small model called the egg model because it looks like an egg produced at, I think, Delft at some point, where we're comparing the aggregate responses of the wells. So this is like we're injecting a fixed volume and we're monitoring the pressure buildup in each well. And when you compare this to an existing simulator, you get basically the right results. Similarly, we can solve a problem that's coupled to multi-component flash. So this is a smaller model representing fine scale resolved fractures on an unstructured mesh. So you are injecting CO2 into a mixture. So basically the SP5 mixture that we used as the benchmark. And then you see that you have high speed of movement through the fractures that's moving up. And you have sort of a two-phase condition in the middle of the model, followed by a sharp shock where you have complete CO2 and you have complete miscibility due to the relatively high pressure of injection here. Compared to basically the MRST code for this that uses, it writes everything in MATLAB, but then it uses linear solves for on the C++ side of things. You get about a 5 times speed up and exactly the same results. This is again a relatively small model, but the sort of behavior is complex because you're solving phase equilibrium at every single point every time you evaluate everything. Another benchmark is the SP9 benchmark. It's not so interesting looking, but it's basically a model that contains a large number of wells and a single injector for pressure support. And as you are depleting this reservoir, these wells change between different controls to make sure that the problem is feasible. And you have gas coming out of the solution. So it's sort of a true three-phase problem with an extra pseudo phase on top, where we have agreement between both commercial simulators and this simulator, which is, it's nice to have, and it's a problem that's quite easy to get mismatch if a well switches at the wrong time or so. So since we then have a bunch of test problems, we can then just do a set of benchmarks. And just running Julia without threads and standard optimization level, sort of the fresh user experience, you get performance that is comparable or outperforming C++ simulators on the same hardware. And many of these other simulators have many hundreds of man years behind them in terms of optimizing and developing for exactly these test cases. So this is quite an encouraging result. So, and here you have models that are very small, 300 cells that run in less than a second, to bigger models that have sort of complex different rock types and many wells that run in sort of 15 minutes. So for instance, if we look at like this model, you can do an LU factorization, and it's sort of, the linear system is not difficult to solve there. But if you go to this, for instance, a bigger model, so 200,000 cells, and then you have a well system on top of it, and you have several degrees of freedom per cell, it becomes quite hard to solve it with direct methods. So what we did is that we implemented what's considered basically best practice preconditioning for these kind of systems. So, and I think I'm going a little bit into the details here because it illustrates some very nice things about the Julia ecosystem. We can define the system as basically divided into two parts, the reservoir and the wells and facility. The wells and facility are really important because they drive the flow, but there are not many degrees of freedom, while the reservoir itself has a large number of degrees of freedom, but is sort of where you want to apply your preconditioner. So this is really big, this is really small, these guys are really sparse, it's just where the wells connect to the reservoir. So when we're solving this system, we don't want to solve the whole thing. And the structure of these systems are quite different because wells are different from the reservoir. So what we instead do is we solve this Schur complement system, where instead of whenever we need to have the action of J times something, we instead compute the Schur complement, which is basically eliminating this block, and then you get this system. So it's supposed to be RR here, actually. It's JRR minus the action of sort of the wells. And equivalently, we saw with the right-hand side becomes then augmented by the wells. And this is like whenever we need a matrix vector product, this guy gets applied, this guy is pre-factorized, and it is quite fast. Now that step, it only leaves us with solving JRR, which is the reservoir equation. And one thing that's particular about the reservoir equation is that typically these preconditions are defined in terms of matrices of matrices. So for instance, inside the fluid volume, if it's a three-phase fluid, then you're going to have three equations, and you're going to have 3 degrees of freedom. And the most efficient way to store this is not to do a full sparse of all the scalars, but to say, hey, I have a big matrix that's matrix of small statically sized matrices. And this was one of the things I was very happy with, is that you take the standard sparse matrix in Julia, you change the type to a static, for instance, 3x3 block, and this just works. Although there is a caveat to this, because most people who wrote various linear solver libraries or preconditioners, they often played fast and loose with this assumption, like A times B is equal to B times A, mostly for floating point numbers. But if these guys are matrices, that's not true. So I needed to patch some things, and you need to be a bit careful when you sort of put things together. But for the majority, this really works, and I think this is a really powerful example of something that I don't think people had tried to do this, but it worked. Yeah, I see I don't have too much time. Talk quickly about the setting in Jutul for variables. Is basically that you divide the domain up into entities, so cells and faces, for instance, for a reservoir. You have a set of variables that need to be fulfilled to set up your governing equations. You can pick some of them to be primary, you're solving for them, parameters, which are unknown, or secondary variables that are things that you can compute from your parameters and other variables. And once you set this up, this basically computes a nice little graph where you have your parameters on one side, you have your primary variables, and then you have a relationship between the primary variables and the secondary variables to compute, for instance, the total masses depend on saturations, the fluid volume, and the densities. Another set here is for like a more complex model that's coupled to a flash. Then you get a lot of more nodes. But the point is you can sort of swap out the definition of each of these nodes quite easily without having to do any structure changes to your simulator. And it makes it quite easy to support, for instance, like different rel perms or densities or functional relationships without having to hard code anything. So I'll finish off this part with a little example. So it's basically relevant to the project we're in. So I made a very synthetic well, and I hope none of you are well drillers, because I might get some criticism. But this is a well that is basically sloping down. And what we're interested in is simulating this. And we pick a monitoring point. We say, OK, this is some distance from the well. We're interested in seeing what's going on, because this might be a place where we don't want the water to go, or we really want it to go. It doesn't matter. We just define an objective function that's just the sum of the water saturation given in the monitor point. So index into the reservoir model, then into the saturation variable. The first phase is the water, and then you pick the monitor point. And from that, it's sort of this standard trick with adjoints. You do a forward simulation, you get a backward simulation, and you get the gradients of this objective function with respect to any parameter you want to look at. Yeah. Maybe I can skip some of this stuff. So basically, to do this sensitivity thing, we then need to have automatic differentiation. We need to do that in the forward way as well. And the structure here is that we really want a pure mutating solution for Jacobians. We don't want to reassemble ever the sparse system we're working with. We don't really ever want to allocate any memory during the simulation. So when we have variables, these are stored as basically arrays that are by default initialized as the forward diff dual type. These are tagged by entities and contain derivatives with respect to the variables in the same entity, to the primary variables in the same entity as a sort of fixed size. So it's sort of on the to-do list to try other AD types here. But the forward diff package is relatively mature and sort of a lot in use. So this is why we use this one. Yeah, it's basically just some fluxes. So once you then compute, so if the properties are local to each cell, then you just call your functions and you get derivatives. But the governing equations depend on, for instance, cells in the neighborhood. So you need to do a little bit more work. So What we do, since we are working with block system, is that we determine the block sparsity structure. So for a given equation defined on an entity, which other entities and what types are those entities does that cell define on? So for instance, a cell might depend on its neighbors and the faces connecting those neighbors. Once we do that, we call basically a sparsity detection on each element for the equation before we start the simulations. We determine what depends on what. And when you are evaluating these things, you just do this decayed view. So you say, OK, I have this AD value, but I'm only going to include the derivatives if I'm looking at this specific point. So you're sort of zooming in on a point, and that makes it trivial to do a global assembly of this thing, because when you have a local state for a given entity index and a given tag, then this thing is it's not allocating any new memory, you're just picking out the value, and you're saying, OK, the derivatives get zeroed out if they don't match what I'm currently looking at. Someone in the lobby? OK, I think that I'm not going to be able to get them in. Yeah, so just an example here of basically if we want to solve this equation using standard finite volume techniques, we just define the flux that's defined as K on each face multiplied by the difference. We take the divergence of the flux, and that's the value of the equation for each cell, and you get sort of automatic setup of a stencil for this. You get something like this if you set up something with boundary conditions, and you get I think even without having sort of put in bounds checks and all of these things you can do, you get about 100 nanosecond per degree of freedom when you assemble it, which I think is reasonable. So finally, in the last few minutes, I'll talk about a coupled reservoir well model. So it's basically the model we're looking at. So we make a reservoir inside the MRST here, where the grid looks quite simple. It has a varying permeability layer. And if we look inside it, we see that the well or the grid is not so simple. It's refined around the well trajectory so that you can have an explicit representation of every single well cell. So you don't, it's sort of fully resolved, and you don't need to do well indices. I'll show a movie here of the visualizations. This is using Makey or Maki or however you pronounce it. So it's basically we are injecting this as a volume rendering. So you see that the well starts to appear and the pressure builds up. And as the pressure builds up, there's also a saturation front moving. We can switch to the saturations and we can look at it again. You see that the saturation is divided up by layers, and there's also gravity effects here. I think I can plot this. Yeah, I can threshold this, and you can see actually how it's moving inside the reservoir. And these plotting tools that are available in Julia, I don't think there is anything open source that's sort of this accessible to doing high quality volume rendering, because we have tried a lot of things, and I think I'm really impressed by the performance there. And since sort of everything is a model, we also have a model for the wells. We can visualize, for instance, the saturation front moving down the well. So the well starts up and we start pumping water into it. That resolves a shock inside here that's simultaneously coupled to the reservoir, and things are moving out. This is, I think, quite powerful when you sort of have the possibility to go into every little part and you visualize it. Yeah, you can do the same thing for wells. This is another test model where you see that you have interactive plotting of all the aggregate responses. And here's an example of then going back to the monitoring point to say that we wonder, we know the water saturation at this point is important to us for some reason. Let's calculate the sensitivity of that point relative to the pore volume. So you have pore volume in each single cell in the reservoir around it, but some pore volumes are important for this point, and others are not. So this is a visualization of the sensitivity. You see that the cells in the same layer where the flow is primarily going, those are really important for the saturation there, so it's no surprise. The other side of the well is not important, also no surprise. But you see interesting things going on the top and below, because you have migration due to permeability and gravity that goes up and down that might influence this point during the simulation. Yeah, it's just an example of doing battery simulation in the same thing, but I think I'll skip this for the next speaker. Yeah, so we have some plans here. I think we want to couple this to other packages. So one thing is that we're working with Julia Hoffman on coupling this to geostats, which is a geostatistical package. We'd like to package it to work against other automatic differentiation packages. We'd like to couple it to differential equations to do ODE solves, to have that as an option, and also some interest in different finite element packages. I think the things that are really lacking on the Julia side here is like distributed memory support, so like MPI solvers, also parallel linear solvers that there's not that much of the standard things you really want that's intrinsically parallel, primarily because they were written before parallel support in Julia was sort of stable, I think. And also interfaces to, for instance, the standard data formats and Python and these things, which is more of an engineering topic. Yeah, I have some more points, but maybe I'll just conclude with the DigiWell thing, and thank you for your attention.